I'm going to show you two ways to do this question. First method, I'm going to label all the dimensions that I have on and then work out the areas of the squares, work out the area of the trapezia, and subtract from the area of the big square. The second method, slightly different tactic involving the diagonals of this quadrilateral. Now, I wouldn't have thought to do it like this, but I looked at the answers and it's really nice. So please do stick around and watch that. Right, so this is 1 and 1. This is 2 and 2, 3 and 3, and then 4 and 4, which means the area of the squares are going to be 1, 4, 9, and 16. And the area of the big square, we're told that it has length 11, so it's going to be 11 times 11, 121. Now I'm going to label the missing lengths. So I've got 5. I just need to think, what do I add on to get 11? This is going to be 6. This is going to be 6 as well. This is going to be 4. And this is going to be 8. Then I have 4 trapezia to find the areas of. And they are trapezia because I've got these parallel sides, one pair of parallel sides here and over here. These are parallel and these are parallel. I'm going to label these A, B, C, and D. And the area of a trapezium is actually a half A plus B times H. You add the two parallel sides together, you divide it by 2, kind of finding the average, and then you times it by the height. I'm not going to prove that here, but this is a formula to learn. So let's look at that for A. Well, it's going to be 1 plus 4, but we have to have it, times by what we call the perpendicular height, 6. Now, actually, we can have the 6. We can decide what order we do things in, so it's just going to be 3 times 5, 15. You don't have to do half of 5, 2.5, and then times that by 6. You know, that's just unnecessarily involving decimals. Just have the even number. And that's going to go for the other one. So for B, it's going to be a half of 3 plus 4 times by 4, which gives 7 times 2, 14. C is half of 3 plus 4 as well, but now times in by 6, which is 3. Oh, sorry, I've made a mistake. It's not 4, it's 2 here. Good that I caught that. So 3 and 2 added together divided by 2 times 6. It's going to be 3 times 5, 15. And then D, a half, 1 plus 2 times 8. So 4 times 3, 12. Brilliant. So then I'm going to add all the areas of the squares up. 1 plus 4 plus 9 plus 16, which 1 plus 9 is 10. 4 plus 16 is 20, so I'm going to get 30 from this. Then I'm going to add up, let me add the A and the C together because that would be quite easy to do. 15 plus 15, that's 30. And then that just leaves me 14 and 12, which is 26, which gives me a total area of 86. Now that is the non-shaded bit, which means that the shaded part is going to be the whole square 121 minus 86. And then I can just add on to 86. So 14 to get to 100, 14 plus 21, that's going to give me 35, and it's centimeters squared. So that's my answer A. Quite a bit to do, but you know, we can slowly go through it in this systematic way. Let's look at a second method for solving this problem. Well done for sticking around. It's really interesting, I think. So it actually turns out that if you have a quadrilateral where the diagonals meet at right angles, then you can find the area of that quadrilateral by timesing the two diagonals together and dividing by 2. Now in this case, because we're across the diagonals of a square, then we will in fact have a right angle, so we're sorted. So what I'm saying is area equals a half diagonal 1 times diagonal 2. Now you might want to think about proving this. I'm going to have a go. So I'm going to purposely make it so it's not a kite, but I'm going to design it so that the diagonals are at right angles here and here. Now, if I say that this length is A, this little one, and this little length is B, and this little length is C, and then this one is D, then I would get that the area is going to equal a half AC, that's going to be this triangle, plus a half AD, it's this triangle, plus a half CB, or BC, plus a half BD. I could factorize out a half, so it's going to be AC plus AD plus BC plus BD, which doesn't really look like it's going to help, except this will actually factorize, because I could write it as A C plus D plus B C plus D, and actually there's a common factor of C plus D here. I can then rewrite it as A plus B times C plus D. Now A plus B is simply one of A plus B is simply one of the diagonals, say diagonal 1, and then C plus D is diagonal 2. So proof is complete. So what we're left with is trying to work out the diagonals of this problem. Now remember, we know that this length is 1 and this one is 1, which means that this length here is going to be, using Pythagoras' theorem, 1 squared plus 1 squared square rooted root 2. And let's do the same for the other ones. This here is going to be 2. So actually the diagonal is just going to be, because the length is twice as much, the diagonal is going to be twice as much. This is going to be 2 root 2. I can take a little shortcut. This is 3 and 3, so this is going to be 3 root 2 for the same reason, and this one's going to be 4 root 2. And then here's the key thing, because the length of the whole square is 11, then the whole thing across is actually 11 root 2. For the same reason, it's just going to be 11 times that original one. I'm using a scale factor. So if I've got 11, then I need to minus 4 and 2 from it. This diagonal is going to be 5 root 2 in length. And then take my 11 root 2 and minus root 2 and 3 root 2. That's going to give me 7 root 2 here, which means that the area is going to be a half times 5 root 2 times 7 root 2. These are going to times together to give 2, which is going to cancel with that half, and we're going to get that answer again, 35. So really nice to see. I hope you enjoyed that as much as I did, and hopefully you gave it a go yourself with the proof. If not, then I hope it makes sense now. Well done.